how to make linear regressions. This is something you may have learned in Algebra 1, but I'd like to take time to review it for now because we're going to need it for Algebra 2. At any point in the video, please feel free to pause it to write down any information that you see. Okay, so scatter plots. Scatter plots are a way to represent bivariate statistics or variables of two variables. Scatter plots are also a set of points that are scattered around the coordinate plane that never connect. So here's an example of data that has comparing height and weight. So if you see like somebody's weight maybe is 52 pounds, this is their height. If somebody is a height of 70, then their weight would be somewhere around 120, 140. So this is a scatter plot. It just literally puts the information on a graph. And what we're going to do today is we're going to learn how to find that line of best fit. So this is something that you may remember from 8th grade, that if I were to draw a line through this, as many points as possible, how could I draw the most accurate line that represents all of those data points? And that's called a line of best fit. And that's what we're going to review today. So let's look first about learnings about something called a correlation coefficient. So a correlation coefficient is a number that designates how close the data values are. If the correlation is positive, like these guys here, they're going up in a positive direction, the correlation coefficient will be between 0 and 1. 0 will mean that the data is spread apart, and 1 means that the data is perfectly aligned. If the correlation coefficient is negative, like these guys, if the data values go like this, down and left, or right rather, then 0 means the data is spread apart, but now -1 will mean the data is perfectly aligned, but in a negative fashion. And a line of best fit, like we kind of discussed before, is a line that best fits the data. So let's do correlation coefficient first. Just so you know, correlation coefficient is always with a value of R. So you will see me use the letter R to denote correlation coefficient. So in this first example, if I were to draw a line of best fit, do you see how the line of best fit practically goes through every single point? And if it does, if it's perfectly aligned, we can say our correlation coefficient, or R, is 1. Now, if I draw a line of best fit through the second set of data points, see how it hits some of them but not all of them? But it's pretty close. The data values are tightly together. So I could say this has a nice correlation coefficient of something similar to 0.95. It's perfect. It's almost perfect, but just not yet. And then this one, if I were to draw a line of best fit through those data points, there is a ton of these data values right here that are kind of away from that line. So therefore, my correlation coefficient here would be a lot smaller. So we could say maybe 0.5 or 50%. It's not perfect. Same kind of values, except for going in a negative direction here. This one, and this one would have a negative correlation. And you can use the same numbers. If I draw the line of best fit, this goes perfectly through them. But now I just say it's -1. This one I'll say is about -0.95 again, because if I draw that line perfectly through, it hits most of the points, but not all of them. And then the last one, my correlation coefficient would be about 0.50, but negative this time, -0.50. If I draw that line through, it hits some, but not all. So the smaller the correlation, the less aligned the data values are. Okay, so now I want to move on to finding that line of best fit. And this is where we're going to need the calculator. The table below shows the results of an experiment that relates the height at which a ball is dropped, so the ball dropping is X, and the height of its first bounce, which is Y. So anytime we have a table that is vertical like this is always going to be my L1 values, and these are always going to be my L2 values. Using the calculator over here, it's not going to highlight it, so I'm going to hold it down. See the stat button? See how it turned black there? That's the stat button. You want to go to edit, which is the first option, and you want to put in your data values. Looks like I've put in the first one, so I'm going to keep going, and you do the same. 90, 80, 70, 60. And then in L2, 26, 23, 21, 18, and 16. Oops. So this is actually good that you saw that. So you see how I've made a mistake somewhere. 26, 23, 21, 18, and 16. It looks like I'm missing a value here. Okay, so I wrote over it, so I have to start back at 100. So 100, 90, 80, 70, and 60. It's very, very important that you check your numbers before you move forward, because any wrong number in this list will make a huge difference with your answers. Okay, so now let's read the question. Part A is saying, write a linear regression equation. That's the same thing as asking you to find the line of best fit. So the way that we do that is we have to hit first, second, quit. We clear everything out. And then we're going to go back to stat. But this time we're going to go over to calc. And instead of that one var stats that you guys normally use, we're going to go down to where it says choice 4, linear regression. And then it's going to ask for where's your X list. So if you look over here, my X list is in L1 and my Y list is in L2. So as long as you have typed that in, which would be second and then L1, that gives you the first list. Second and then L2 and then 2 gives you L2. Your frequency list will always be blank, and your store regression equation you don't need. So we can just go ahead and hit calculate. Perfect. So now we have our Y equals AX plus B. That should be something familiar to you. AX plus B is similar to Y equals MX plus B. So this is normally what you're used to when we have a line, Y equals MX plus B, except now the calculator uses AX plus B. Same thing, A is still the slope and B is still the y-intercept. So Y is equal to 0.25 for my A, X plus 0.8 for my Y. Now, this R that you see in the calculator screen, the R is that correlation coefficient that we discussed. So this R, if you read the calculator, says 0.99 or if we round it maybe 2 decimal places, we could say, let's do 0.998. Let's round to 3 decimal places. That is your correlation coefficient. Now, if your calculator screen doesn't have the R, that's just because you didn't turn your diagnostics on. So what you can do is you can hit second and then catalog, and then go down to where it says D for diagnostics. I can do it a little bit easier here. You guys will just have to scroll down, and I guess this calculator version doesn't have it, but yours should say diagnostic. So take your diagnostic and turn it on. There is another way to get to it. Let's see, if you hit second quit and you go to the mode, it should be down here somewhere. It may say diagnostics. All right, I don't see it. If you have trouble, let me know. I can send you the information of how to do that. But that's how you would get your correlation coefficient. Okay, next, part B. Part B says, using this equation, find the bounce height. Okay, so they want the bounce height given that we have a drop height of 0.75. So if you look back at your table, your bounce height is Y. So that's what they want us to find. Bounce height is Y, given that my drop height is 0.75. So let's rewrite our equation. Y equals 0.25x plus 0.8. And we want to find the bounce height Y, given that my drop height is 75. So I'm plugging in 75 into my X value. And I'm just going to type this into the calculator. So 0.25 times 75 plus 0.8. And I get about 19.55. And I believe that's in centimeters. So that would be my final answer. And we could use our table of values here to kind of, estimate that, if you would. If I have a drop height of 75, wouldn't 75 be somewhere around here, right? In between, that was between 60 and 70. So between 75 would be probably right here, right? That would be a drop height of 75. Therefore, my bounce height would have to be somewhere in between 21 and 18. So we're good. We got about 19.55, so that works nicely. Okay, let's try the last part. The last part says, using the equation from part A, find now the drop height. So the drop height is x, given a bounce height, y. So I'm going to start by writing the equation again. Y equals 0.25x plus 0.8. And I have a y value of 10, and I want to find my x value. So just minus 0.8 on both sides. 10 minus 0.8 is about 9.2, equals 0.25x, and divide by 0.25. All right, that I can't do in my head, so 9.2 divided by 0.25, that gives us x, which is 36.8. And we could theoretically look at our chart again to see if this makes any sense. So we're looking for a bounce height of 10. Well, a bounce height of 10 is outside the data values, so we know that if we follow this trend, 100, 90, 80, 70, 60, it's getting smaller, so it has to be smaller than 60 for it to make sense. And I believe it is. Yep, 36.8. That was our final answer. All right, that's it today for linear regression models. If you have any questions, please let us know. All right, thank you so much.